right, let's get started. Hello, everybody. A couple of people still trickling in. Hopefully you guys are good. Got some news. So a date has been chosen. The math finals are on the Thursday date that I mentioned. So that is now for sure. Let me pull this thing up. Okay, so hopefully you guys can see that. I'm right here. I'm gonna head out. Yeah, so let's actually put that up somewhere. So math 212 final, and I'll email the other classes this info. But this just came in a few minutes ago. So it is reading it off, making sure I don't make any mistakes. Yeah, so the 212, the finals for 190, 212, 346, and 392 are Thursday, May 21 at 3:30 to 5:45 p.m. So, yay! Should have like a confetti animation here. All right. Mock will probably be posted tomorrow. Yeah. So I actually want to crash early tonight because I didn't get much sleep last night, and yeah, not great. Okay, so I'll probably post mock tomorrow. That is for Wednesday. And yeah, so the final is going to finish. Let's actually jump into it. So the final is going to be on Thursday, May 21st, 3:30 to 5:45 p.m. And like with the mock, as I mentioned in an email, I think I want to push our extra class to this Friday instead of next Friday, because then I'll be pretty sure to actually finish. So today's class, I think, is one of two remaining classes where I'm going to finish material. So I want to finish talking about limits today. We'll start partial derivatives today, and then I want to finish talking about partial derivatives on Friday, and then we're done. And then so next week, we just have tests and final preparation to deal with. And then the following week after that is the final, the following Thursday. So I think that works a little bit nicer. It's a little less cramped, give us a little bit more space. So that's what I want to do. As for the, no surprise today. The surprise last time was a lot of fun. I had a lot of fun with it. Anyway, so yeah, extra class on Friday. I already sent the doodle poll. It seems like more people can do it earlier in the day this time than last week. So we'll do that. I'll get you guys the date. I'll leave it open for till tomorrow, I guess, and then I'll let you guys know. But yeah, I'll post the review for the next test tomorrow. Next test is on Wednesday. That covers the second half of the course. We are having an extra class on Friday this week, and we are having our final on Thursday, May 21st. Yeah, as well as another activity I want to do on Friday is I actually want us to check out the Blackboard. So there's this random sort of mock quote unquote test going on Blackboard. It's not really a mock test because the questions don't actually pertain to any one class. It's just a test I'm going to load into Blackboard, have it set up. It's already set up to be launched on Friday. I have it set up so that you guys are going to go into Blackboard. You're going to do this fake test. It's going to take like 10 minutes of activity. We'll definitely have 10 minutes extra left over, I think, on Friday. And so we can do that then, just to get you guys to know where to go and how to go. Make sure you can go into Blackboard. Make sure you know where to go, where the final is going to be. So we're going to do practice of that on Friday as well. Yeah, like during class. I'll do it during class because it's going to be like a 10-minute activity. The fake Blackboard test is set for like 10 minutes. So I'll literally just like sit and wait on you guys after a while. And then you guys can give me feedback, making sure everything is working correctly. And if you have any issues, we can deal with them right up front. Yeah, that's all the kind of new information I have for now. Let's get into the material. So we started talking about limits last class, and we understood that limits were a little bit harder to get to work in higher dimensions because we don't only need to concern ourselves with two directions, the left and the right, which was all that mattered in 2D. Once we are going to 3 dimensions and higher, we have 2 variable limits. We can approach a point from any direction, not just left and right. So we kind of have to have things a lot tighter. We have to have our eyes on a lot more things, to put it mildly. Then we kind of went into the topic of showing how a limit does not exist. Because every path going to a point needs to agree, just finding any 2 paths that don't agree is enough to make the limit not exist. So actually proving that a limit does not exist is actually a lot easier and a lot more straightforward in general. So whenever a limit does not exist, all you need to do is find 2 paths that don't agree. And we had this strategy of how we want to pick these paths to get the best results in the shortest amount of time. First thing is to try an obvious path. Just let one variable at a time approach its own coordinate. So if you want x comma y to approach a comma b, you can try let x go along a, but let y inch closer to b. Or you can let y equals b and let x inch closer to a. And so you just do like one at a time and see what happens. A lot of times that'll give you a result. Now you don't want any redundancy here because the point, if you want to show that a limit does not exist, you do want to not get the same answer twice. You want to get a different answer. So if you realize that the 2 obvious paths are going to give you the same answer, you just skip one. Move on to the next thing. The next thing, if after trying the obvious paths, is to try a path that allows you to combine something or take advantage of some formula. And that is how we can move forward. So we tried here with this equation, with this limit here, we traveled along x equals 0. The limit gave us 0, and we traveled along y equals x, and the limit gave us a half by actually plugging these values into the limit. And it's of course important to know that the path must travel through the point that we are caring about. Then eventually we got to, did several examples, and we got to this one. Went through the obvious path, x equals 0. Y equals x would be the next thing that we should try, but that also gave us 0. 0, and at this point we kind of realized that we've been bamboozled. It actually exists. And so now we're going to talk about that situation. How do we show that a limit exists? So that's what we're going to do now. Talk about the existence of limits. All right, but some more things to do in mind. When assessing the limit as x, y approaches a, b of f of x, y. So 1, not sure, check if limit does not exist first. Okay, so as I mentioned, sometimes they would ask the question in this kind of open-ended way. Here's a limit, determine whether it exists or not, and prove your claim. They can ask the question like that. Right? And you'll go do that like how I said, try to find 2 paths to get a different answer. choose the paths in the way I mentioned to you, and within 2 or 3 trials, you'll be able to have a pretty good suspicion as to whether it exists or not. You should definitely be able to show it not existing based on the strategy I gave you before. So try to show it does not exist first. Another thing to keep in mind, you must choose paths that pass through AB. So example, if AB equals 0, 0, then x equals 1 is an invalid path. So make sure the paths that you're choosing actually go through the point. So that's very important. Follow the strategy to stay efficient. I'm not sure if these strategies are written down anywhere. Sometimes I give you guys strategies. It's just from my own personal study. Like after doing dozens, hundreds of limits myself, I kind of realized if I think of it in these 2 ways, I tend to get to the answer a lot faster. And these strategies have been battle tested. So I won't say they work in the general sense, but in the kind of problems that you'll see in the typical calculus book, these are kind of what you want to have in mind. Go across the obvious path, go through x equals a, y equals b, then try to choose something that allows you to combine terms or take advantage of some known limit formula, like the limit as x approaches 0 of sine x over x equals 1. Things like that you should remember. And if you see a way that you can shoehorn that in there, you take advantage of it. Then, if suspicious, the limit exists, prove it, if possible, and make sure that you actually have the correct assumption here using below. All right, so here is how we're going to talk about showing that a limit exists, actually finding a limit. Now, technically speaking, to actually say that a limit exists, we have to actually show this definition is going to work out. However, that definition is very hard to work with, the epsilon delta definition in higher dimensions. So we're not even going to do that. There are easy examples I could give you, but for a lot of the problems that we will be seeing, it's going to be actually hard to get it to work. So there is a workaround. There is a theorem that says using the squeeze theorem, we can actually determine the value of limits. Now, it's going to seem a little bit strange at first, so I'm also going to explain to you why this works, but trust me, it actually works. So suppose we have a function defined close to the point AB, right? So finding the limit is a thing we can do because we can get arbitrarily close to the point. We know we can actually examine the. There is a function g of xy. So g of xy is not a function that you would have off the bat. G of xy is going to be a function you have to find. You will need to find this g. So it's not going to be given to you. But if you can find a function such that the following is true, f minus L, L is your proposed limit, right? It's what you guess that the limit is. If you can take f minus L in absolute values, and it's less than or equal to some function g, which you might have to look for, and at the same time, if you take the same limit, taking the same limit as the original problem, Meaning, if you started out with a question limit as xy approaches 1 comma 2, then you need to take the limit as xy approaches 1 comma 2 of g, okay? So if you can find a function such that f of xy minus L in absolute values is less than or equal to g, and at the same time, taking the limit of that g gives you the result 0, no mistake, it's definitely 0, then you will be able to conclude that we can conclude this. We can conclude that the limit is L if we can find this function. Okay. Now we're going to talk about how to find this function later on, but let's actually talk about why does this even work? So here's why it works. Suppose we could find such a g. Then this means in absolute values, your f minus L is less than or equal to this g. Well, that would mean if you unfold this, minus g is less than or equal to f minus L less than or equal to g. But that means you can add L to both sides. So here you have g plus L. Here you'd have L minus g. That's kind of way out there. And now what you can do is you can take the limit of everybody. So I can take the limit here, limit here, limit here. Now, of course, since the limit of g approaches 0, and we are taking the limit of the sum, which is going to be the sum of the limits, this side here is just going to give you L. And since, again, the limit of g is 0, this side here is going to give you L. L is just going to be some real number. And so you have the limit of f is squeezed between L and L, which means the limit of f must be equal to L by squeeze theorem. So here we can actually use the squeeze theorem to help us out. If we can find a function that has these two behaviors, we have found a way that we can prove the limit exists. And this absolute values here for us, of course, in 3 dimensions, absolute values does represent the distance away. So it's the distance from any direction. If I can bound the distance between the Z output and L by this function G, and that function goes off to 0, it means the distance between the Z output and L is 0. They are the same. So the output is going towards the L. And that applies because of squeeze theorem. So that's a very nice theorem here. Now you might wonder, how do you find such a G? And how do we actually get this to work? So I have some examples here which we're going to go through, A and B. And then I thought, you know what, wait, hold on, wait. Let's do this guy, right? That's the guy that made a fool of us last time. So let's actually do him first, right? So let's start there. So Kevin, where did I miss you? You said your internet messed up. Basically what I'm saying is if we can find a function g such that f of xy minus L is less than g and the limit of g approaches 0, then the limit of f must be equal to L. Oh, so in the proof, you don't really need to know the proof, but I'm just showing you why it works. If I bound it in absolute values by g, I know by property of absolute values, I can break the inequality into 2 parts. Add L to all sides, take the limit of all sides, I get L on both sides because the limit of the g part goes to 0. And then I just have the limit of f is between greater than or equal to L at the same time. You have to actually be L. But remember what f is measuring. F is measuring the z output. Z equals f of x. So this is basically saying the Z value is becoming L, right? Not the death note L, just the actual L being the proposed limit. Okay, so here are some examples. I'm going to show you how to work this out. But we're going to do this guy, which, you know, Kevin threw at us and was, you know, was totally leading us astray here for a while. Okay, so let's do this guy first. Right? Okay, so this was the guy that was messing with us on Wednesday. Let's end this man's whole career. All right. So we think the limit is 0, right? Zero. So this means we need to find. So once you come up with the suspicion that, oh, hey, maybe this limit is 0, then here's what I want you to think. Here's your next train of thought here. Once you say, you know what, I tried all these obvious paths, I think this is actually the limit. We need to find a g of x, y, such that if I take the function and I minus the 0, which is the proposed limit, right? So here we think the answer is 0. Because sometimes 0 can show up in several locations. I want you to know which 0 you're looking at the time. Such that f of x, y minus 0 is in less than absolute value than g of x. And at the same time, g approaches 0, then the limit is 0. As in the 0 that's here, the L. Okay? So how do we go about finding such a 0? And it turns out the same sort of skill set. So this is a skill set that we've used like 2 times before. We used it back in Calc 1 when we were trying to prove limits using squeeze theorem, and we were kind of creating things that would be bigger than or smaller than something, creating inequalities out of thin air. We saw this in this class again when we were doing comparison theorems, trying to figure out something that's bigger than or smaller than something else. So the same sort of manipulations you were doing then is the same sort of manipulations you're going to do now. You're going to try to figure out a way to make, if you take the expression f of x minus L, try to figure out a way to make things like the denominator smaller. This is going to give you something bigger, making the numerator bigger in a convenient way. So you're going to try to do things like that. You're going to do these little tweaks that you've learned how to do in an effort to get the inside to be less than or equal to something. But you're not going to just do this completely at random. The thing you want to end up with should be a thing that you can clearly see the limit is going to 0, no ambiguity, it's definitely 0, right? So that is the idea here. Okay. So David has a guess. He's like, oh, set x squared y squared over x squared plus y squared equal to g. G, that's a problem. Because that, if we're getting close to 0 and our y value is getting close to 0, then y squared is going to be smaller than y, which means you've just made the numerator smaller. So you have to be careful. So yeah, so let's actually look at this. So you can make the numerator smaller, or you can make the denominator, smaller or the numerator larger. So that's the goal we have. So that's what I'm going to do. So I know I'm trying to find this g, all right? So here's what I'm going to do. I'm going to set x squared y over x squared plus y squared minus 0 in absolute values. Now, of course, that is going to be, it's just subtracting 0. Now I want to be able to find something that's bigger than that. Okay, so another idea other than squaring the y, because squaring the y, when you're less than 0 in absolute value, the square actually makes you smaller, right? A half squared is actually a quarter. Right? So your square is only bigger than the original number, you know, when it's greater than 1, right? Or the number is negative, but we're worried about positive numbers here. So how can I make this bigger? Any other ideas besides squaring the x squared alone? Like what is your, how do you get to x squared? I think Kevin has a nice idea. Ignore the y squared in the denominator. That is definitely greater than or equal to, right? So y squared is going to be a positive number. Okay. Oh, did Evan suggest that before? Okay, so you can do that. The denominator now is potentially smaller because we have subtracted potentially a positive number. Now, if your y happens to be equal to 0, we know we're not even considering that because that didn't help us. That would make the numerator 0. So we're not even assuming the y is getting to be 0. The y is something else. And that therefore we just made the denominator smaller, which means the fraction is bigger, which also means I can start to simplify, which now means this guy is actually just the absolute value of y. And what can you say about y as x comma y approaches 0? This approaches 0 for sure. I know, for sure. Okay, so choose g of xy to be this function. Then it means that the limit as x squared y over x squared plus y squared is equal to 0. This 0, the one that was over here. And that's it. That's the proof. It almost seems like magic. I understand it seemed like, well, we really didn't do much. We kind of just ignored something and our problems fixed itself, which, yeah, I know. In general, that doesn't work. Don't ignore your problems. They won't fix themselves. But in this case, it works because of the magic of squeeze theorem, right? If I can find a function that behaves this way, the function absolute value of y, is actually larger than x squared y divided by x squared plus y squared. And at the same time, that function approaches 0 as xy approaches 0. And that's it. We've actually proven that the limit is 0. This actually shows it from all directions, believe it or not, because of the absolute values. Okay, that's it. Let's actually try it on these two. So now you guys try, and it's not a trick. This one exists. Okay. Actually try it on this one. So first, pretend I did not tell you the answer. So pretend I just gave you this problem. Say, oh, determine whether or not the limit exists. What would you try to do? Yeah. It's going to be the case now. Whenever I don't say I'm not tricking you, everyone's kind of going to assume I'm trying to trick you. Yeah, this is why math people get a bad rap. You know, teachers trying to trick me, and sometimes it's just like very straightforward. But a little skepticism is good. Okay, go along the easy path. So so test paths to see if it did any. And are you guys good? Are you guys hearing me? I got a message now that like internet is unstable or whatever. So there's no lag or anything, hopefully. Then we can go I don't know, should I disconnect and reconnect again? Because I don't know. Let me disconnect and come back. I don't know if it's my internet or it's something else, but I keep getting this message. All right, let's get back at it. All right. So okay, now let's go along another obvious path. Is probably going to be the next thing. So if we go along y equals 0, we're going to get 0, but let's do something interesting. Let's do something like along x equals y, or y equals x, whatever. So the limit is going to be, I'm thinking of, say, x comma x approaches 0 comma 0. So this would be 2x squared sine x divided by 3x squared. And then these guys would cancel. Now, of course, your sine of x is going to approach 0 as x approaches 0. And so this again gives you 0. Now, once I pick these two paths, suspicious that exists. Suspicious. So now you say, maybe the limit is 0. And so immediately what I need to jump into now is I go in and I throw in these absolute values and I put that thing. So 2x squared sine y over 2x squared plus y squared minus 0, which is what I think the proposed limit is. This 0 is the guy that I put here. And of course, I can just ignore the 0 if I'm subtracting 0. Now, if this were a number, I would combine the fractions here. Okay. So you were solving for D&E? Well, you should have realized that you would get 0 all the time. Okay. So At this point, yeah, as someone recommends, get rid of, say, the y squared in the denominator again. That would create something larger, potentially. That would cancel. And so we would have here the absolute value of the sine of y. And that approaches 0 as xy approaches 0, 0. So this means the limit of 2x squared sine y over 2x squared plus y squared is equal to 0. And you can write by squeeze theorem if you want. Now, these guys will move down. But that's going to be something cool that I'm going to show you later. So here, suspicious that the limit is actually 0, and we just proved it by the squeeze theorem. So that's clear. What about this one? Shouldn't have cut it and put it in. Now it just seems like I'm just randomly going into questions. Let's leave these guys here. Okay, this one. What do you think for this one? That's throwing out to you guys. What does that mean? What is the first thing you would do? Like, that's a problem that you see. What would you think? So remember, when you're setting up the absolute value, you have to have a limit in mind, right? So you have to have some value that you want to put in the absolute value, the function minus that. So you can't really try to set this guy up before getting such a value. And so you have to actually come up with a theory. So you kind of have to check a path anyway. So that's not just something that check for DNE. But yeah, if it's your intention, you can check for it. But there's actually an intention that I would see ahead of this. One thing I would realize is that the top I can use difference of squares. You see, the top is x squared minus y squared times x squared plus y squared. So we've been tricked yet again. We've been foiled. It turns out our little Calc 1 magic can deal with this guy. No squeeze theorem necessary. We're pretty sure that's 0, guys. Yeah, so just factoring. You guys got to be on your toes, man. You guys got to be on your toes. Now, we could have done the absolute value thing. So I'm going to do it for fun. We could have but it would be less efficient. So for example, someone can come in and just like brute forcing, they're all about the strategy, and I'm not going to do anything other than going through this strategy. So one thing you could do is you could come like along x equals 0, and your limit would look like the limit as xy approaches 0, as 0y approaches 0, 0 of. If your x equals 0, you just have minus y to the 4th over y squared. You would get minus y squared, and of course that limit is 0. And then you can do something like along x equals y, and right away you would get that the limit is 0 over 2x squared, which is 0. And at this point, suspicious. So you would jump into setting this guy x to the 4th minus y to the 4th over x squared plus y squared minus 0. And then you're going to be like, well, how can I make this guy less than or equal to something simpler that I know? Now we could think the route of, let's get rid of the x squared or the y squared from the denominator, but you'll realize that you'll result in a division by 0 if you make either of these choices. Because if I leave the x squared and take away the y squared, the x squared is going to divide evenly to the x to the 4th, but then I'll end up with a term that's y to the 4th over x squared, so not very useful. So ignoring the x squared or the y squared won't work, right? You'd result in a division by 0. So at that point, you would kind of do what we did earlier anyway, factor. Cancel. And we have this guy. And that approaches 0. And so you choose g equals that function. Now, of course, equal is included in less than or equal. So the theorem is still fulfilled and you can get it that way. But as you can see, that was a lot more work, right? So if you just kind of run into this blind, just kind of doing things without thinking about it, you miss the opportunity for like a one-liner here. Okay. Yes, G always has to go to 0 specifically. Right. So that's why I kind of highlighted the zeros here, because this 0 doesn't have to be 0, it can be anything. But for this theorem to work out, for this strategy to work out, the G function must always hit 0. So regardless of what L is, G must approach 0 specifically. Because that's what allowed us to apply the squeeze theorem. So you could do it here, but it was overkill. Algebra can help you. So this is kind of a nice way for me to segue into some other things that I want to say about limits. All your old limit tricks still actually work. So it's still valid to just plug in the coordinate if you're not going to, if the thing is continuous, right? And I'm going to talk about what continuity means in a little bit. Just remember how when you were doing Calc 1 limits, you had this strategy, at least if you were in my class, I gave you a strategy. Try to plug in is the first step. If you get an answer, great. If not, try to simplify to see if you can plug in. If not, then you try to do one of the special techniques like a squeeze theorem or a trigger or something like that. Then you know if it looks like a rational function, you can do, oh my God. There's a whole other thing. There's a whole thing. If you weren't in my class, I can rattle off the steps, but then you'd probably be confused. Okay, so there's a strategy that you had from Calc 1. That strategy can still essentially work. So the first thing you would try to do for any limit is actually just try to plug in. Now, we couldn't have done that with anything that we've seen before because we'd have division by 0. But your second thought should always be, could I simplify it so I can plug in? It turns out that up here, we couldn't really do that. Like, there was nothing to simplify here. And so that's why we're forced to go through this strategy. But yeah, so things like of that sort plug in. So, and we now have other tricks. So this is something cool I want to show you, and I'm going to do one example and show you how it works, and then maybe you can do the other one. Polar coordinates. This is something that we've learned this semester. You could actually use that to show a limit exists in some cases. How can we use polar coordinates to help us? So recall in polar coordinates, x equals, y equals, I think I'll leave this to you guys. What is x equal to in polar coordinates? Throw in a little bit of polar review here. X equals r cosine theta. Y equals r sine theta, and then x squared plus y squared would equal r squared, right? So this is r cosine theta. This is r sine theta. And this is r squared. Now, note, as x and y approach 0, we have that r will approach 0. So that's something important to consider. But at any given time, I can switch to a polar coordinates way of looking at the world, and these three equations here will take effect. How do we use this to our advantage? Let's look at this guy again, right? The guy that made a fool of us last time. So we said we were going to end his whole career. We're going to end him with a whole other method to show him he ain't nothing, all right? So here's one way to do it. Switch to polar. What does this mean? Well, it means that the limit is, as x, y approaches 0, 0, it's the same as me saying my r value is approaching 0. And then wherever I see x squared plus y squared, I can replace with r squared. Wherever I see x's and y's, but they're not in the x squared plus y squared form, I just replace them with x with r cosine theta. So this would be r squared cosine squared theta. And my y would be r sine theta. So this here is the limit as r approaches 0. So now I can essentially think of this as a single variable limit. Now, of course, the theta here, for our intents and purposes, will be thought of as a constant. It's not something that the limit cares about. The r's would cancel. And so I now have the limit as r approaches 0 of r times cosine squared theta sine theta. Now, of course, my r is going to 0. So I have 0 times this constant. So that's 0. This guy over the side. Okay, so here you can see we can completely switch a problem over to polar coordinates. Ah, Zarif, wow, you like that, huh? Yeah, it's really cool. A lot of times polar coordinates can help you. And when you get to the next class, you're going to learn something called cylindrical coordinates. Those can help you with limits as well, even though typically in a calculus class, they never really talk about it, but you could, right? Whenever you learn a new coordinate system, there are many situations in which you can find yourself in which switching to this new coordinate system can really make things easier. Here, we can literally go from a higher dimensional limit to a one-dimensional limit just by switching to polar. I don't have to worry about what both x and y are doing. Now I just have to worry about what is R doing? What is the sum of x squared plus y squared doing, right? And that's a very nice way of dealing with it. All right, now you guys, yeah, no, it's pretty cool. It's pretty cool. Blows my mind, and I already know about this stuff. That this actually works out. So yeah, all right, you guys, what do we want to do here? It is always applicable. So there is nothing that could stop you from actually applying polar coordinates. It's just a matter of would it be useful to you or not, right? So especially if you don't see like an x squared plus a y squared, there's nothing that would give you a nice form, because sometimes you can switch all your x's to r cosine theta and all your y's to r sine theta, and it either doesn't help or it actually makes your situation a lot more complicated. In this case, it actually made our situation simpler. So it's not that it's really illegal at any given time, it's just that sometimes it doesn't really help. Right? But polar coordinates, it's a valid way to look at the world at any given time. It's just a different way to locate coordinates. Instead of thinking of it in terms of rectangles, you think of the world in terms of circles. There's nothing wrong with switching the mode of thinking. It's just that a lot of times now it is convenient, which means here, switching to polar, someone already said it, the limit would become r approaching 0. Everywhere I see x squared plus y squared, I can replace with an r squared. So now I have this single variable limit. Okay, so what is that limit? Geez, I'm running into more examples here. I'm writing too big. Okay, so this is a little more review of Calc 1 limits. How would you do that limit? Log of 0 is undefined, but remember, we're approaching 0. We're not at 0. And in fact, we are ln'ing a square, right? There's a square inside of the ln, so the results are always going to be positive as you get close to 0. So you think of this as you're approaching 0 from the right, right? So what happens to ln x as x approaches 0 from the right? It's not DNE technically. It does not approach 0. Think of the graph. Does not approach 1 either. Think of the graph. What does the graph of ln look like? Never forget. Never forget. Graph of ln looks like this, right? It's the inverse of the exponential. It passes through 0 at 1, and then it goes down to negative infinity. So this guy is actually approaching 0 times infinity. Negative infinity specifically. So this is indeterminate. Now, you learned a situation of how to deal with indeterminate forms back in Calc 1. It's not the same as DNE. This limit actually exists. Right. So Zarev says you use L'Hopital's rule. Now, L'Hopital's rule only works in what? 2 situations, right? Is 0 times infinity one of those situations? No. Geez, Kevin, you're just walking into it today, huh? L'Hopital's rule only works for specific indeterminate forms, 0 over 0 and infinity over infinity. So before you apply L'Hopital's rule, you have to write it in the form 0 over 0 or infinity over infinity. And so the next step would be something like this. Leave the ln where it stands, move the r in the denominator by taking it to a negative power. Now you'll realize that this approaches infinity over infinity. Well, negative infinity over infinity. So can use L'Hopital's. L'hôpital. The reason why you guys forgot is because you never said it with a French accent back in the day. All right, so you apply L'Hopital's rule. L'Hopital's rule says if we have the limit approaching 0 over 0 or infinity over infinity, we can differentiate the top and differentiate the bottom. And if that limit exists, it's equal to the original value of the limit. You will notice that if we simplify, becomes minus r. So the limit is 0. Well, the s is silent, minus r squared. So it's really like l'hôpital. But if you don't write that, you can write it as this, because I think it's actually French for hospital. But if you do this, you don't pronounce the S, technically. I know a lot of people pronounce the S and they call it hospital, but they're not supposed to. Timothy Chalamet, yeah, that's another one. Yeah. That dude should definitely make like a math theorem and have kids butcher his name. Just like they did it to Euler, they do it to L'Hopital, they do it to all the greats. Even though L'Hopital never invented L'Hopital's rule, it was invented by Bernoulli, but I digress. Okay, so Calc 1 methods still work. You can actually use polar coordinates to switch to a Calc 1 version of a limit. No, it's Euler. Okay. Yes, it's pronounced like Euler. Okay, so what else? Did I miss any? So these guys. Geez, running out of space. Anyway, I do want you guys to recognize that, geez. I don't think that actually got all of it. I do want you guys to recognize that things from Calc 1 still apply. And every now and then, they'll be a little bit sneaky and throw one of these limits at you, when really, you don't even need any of the techniques that we learned in this class. You can use Calc 1 techniques and get to the answer. So that's why I chose some of these examples that will allow me to remind you about some techniques from Calc 1. So other things from Calc 1 that you should know works. You're still allowed to just plug in, right? So if you saw an example like this one, this limit randomly shows up. Oh, determine whether or not the limit exists and prove your claim. Dude, you can prove it by literally just plugging in zeros. Because in this case, you don't divide by 0. The answer is just a quarter, right? So pay attention. Don't just jump into a strategy just because you know what, the squeeze theorem is a really cool strategy. That's clean, man. I'm always going to do that. No, have a little bit of discernment. It's kind of like those problems back in Calc 1 when they had you to differentiate a logarithm, and a lot of people just run into u prime over u when it's really complicated. You should have first applied the rules of a logarithm, make your life simpler, then apply the derivative formulas. So whenever you can, simplify first. If you're faced with a limit, the first thing you should try to do is plug in the numbers. If that doesn't work, try to simplify so you can plug in numbers. Can I factor and cancel anything? And if that doesn't work, now you try, oh, let's approach from this direction, that direction, see what the limit might be. And then if you believe it exists, apply the squeeze theorem. You should kind of go through these beats in your head. Now the Calc 1 version, I kind of expect that to happen almost automatically at this point. So I'm not really going to emphasize that part of the strategy. But there is a whole Calc 1 strategy that precedes all this. If you see any of those guys, if you see like a L'Hopital's rule can work, or a plug-in can work, or a factoring and cancel can work, you do that first. You don't have to do these things. Okay. These are just some techniques for when those guys, the calc limits are a joke now, are a joke. Very clever use of words. I don't know if you intended that pun. Yes, Calc 1 limits are that they are a joke. If you look back at them and remember all the yeah, you remember when Calc 1 used to make you rip your hair out? Yeah, those were the days. And I also showed you an example like this, but here's another one. Simplifying and plugging in also works. So these are just some things I want you to have in the back of your mind. So just know that old techniques can still work as well. So here, I can't plug in 1, 2. Can't plug in because division by 0. So then I ask myself, can I simplify? And so now you try to look at it. Could I simplify? So put that in green. So xy is approaching 1, 2. I could factor out a common y from the top. Then, of course, you recognize that as the difference of squares. So the answer is yes, you can simplify. So now you're left with the limit as xy approaches 1, 2 of y times the radical of x plus 1. And so this limit here is just 2, 4. Because the y goes to 2 and then the x goes to 1, so this 1 goes on to 2, that's 4. So that limit is 4. So those strategies, they all still work. Remember your Calc 1 limits, kids. No, there's no real way to not write the notation, which is why sometimes I just get lazy. Sometimes I just get lazy and just write LIM in places. Like you'll see me write it sometimes. Yeah, like just LIM. Whenever it's understood. Like I said, you're allowed to be a little bit sloppy here. Now, this is a nice segue into other stuff that we would like to talk about. Continuity. Now, again, not going to talk really too much in technical detail here because one, you don't really have to know it, but two, just to remind you, sometimes the ideas can be important. Continuity, it kind of means the same thing what you think it would mean. So when do you think of switching to polar coordinates is the question. So yeah, like I would say, if you want to do a general approach to limits, I would kind of go back to the Calc 1 strategies that I gave you guys. I mean, you can go back to my 201 lectures and just kind of filter in the Calc 3 stuff after that. So if I'm faced with a random limit, I'm definitely going to look, can I plug in the number? No. Can I simplify to plug in the number? No. All right. So now you have to think of it as a Calc 1 limit. Now you try to see, let me try to make it not exist. Then you try to see if you think it's a limit, you try to use the squeeze theorem. Or if you see expressions like x squared plus y squared or something like that, you can try to apply polar coordinates. So I wouldn't randomly go in and apply polar coordinates. It will work in a lot of cases, but normally it's when something jumps out at you, right? Like you see an expression that reminds you of polar coordinates. Yeah, sometimes you can't erase the problem to make it not exist because some of your problems will be on the computer. So unless you're gonna like throw your computer out the window or turn the screen off, both of those would be bad. So sometimes you have no choice but to actually go through it. All right, Now, moving on to continuity. Essentially what we think of this as, it represents a function that has no breaks, no gaps, no holes, no nothing. So we say it's continuous at a point if, you know, it's very smooth at the point, there's no disruption. However, that's not a good mathematical definition. The mathematical way we defined continuity at a point is if the limit exists and it equals the value of the function at that point. Whenever that actually happens, that means all those nice things that we interpret as continuity will also happen. So the same thing is true for continuity in higher dimension, right? So f of xy is continuous at a comma b if the limit as xy approaches a comma b is equal to f of a comma b. So the output of the function is equal to the limit as you approach the point. We say it's continuous in a region if it works for all points, if this equation holds for all points in that region. And we say the function is continuous, period, if this equation works for all points in the domain of the function. Okay, so that's what continuity means. The limit equals the value of the function at the point. Okay. Now, there are some things that you need to remember about limits and continuity from single variable calculus, just some ideas. I copied them down here, but we probably don't need to talk about these in detail. But you definitely want to read these and make sure you remember all this stuff. You'll see it in the notes. Okay, so 3 things need to happen for a limit to exist. The function must be defined, the limit must exist, and both of those must be equal. So that's like a 3-step checklist. That was something that you saw in Calc 1 as well. That still works here. And a lot of facts would work out for limits and continuity that you expect. So combinations of continuous functions are continuous. So x times sine y is a continuous function because x is continuous, it's a polynomial. Sine of y is continuous because it's a sine function. So the product is continuous. So you can take different combinations of continuous functions to create other continuous functions, as long as the combination itself doesn't introduce something like a division by 0 or a negative under a radical. Limits can pass through continuous functions. So if I'm taking like the limit of the sine of x squared, I can think of it as the sine of the limit of x squared. I can take the limit and phase it through the sine function. Or if I'm, so that these, maybe I'll write that one. So limits pass through continuous functions. So I mean, for example, like the limit of e to some function, well, that's e to the limit of the function. Or the limit of the sine of some function, well, that's equal to the sine of the limit of the function, right? Things of that sort. You can move limits through continuous functions. You can factor constants out, all that good stuff. The extreme value theorem still holds. We're not going to talk about that at all in this class, but you will talk about it in next class because, of course, finding maximums and minimums is going to be important for us in calculus in the higher dimensional case, just as it was in the single variable case. So you are going to talk about finding maximums and minimums of all these functions, which now, that reminds me of something I wanted to say earlier. Although, I mean, it was just something that's nice to see. I don't think it's necessary completely. But now there are lots of these that are around, but this one I think is nice. Let's go back to that guy, the one that gave us trouble last time. Was it our guy? I think I actually put him back here. Yeah, let's do this guy first. Or we'll talk about it when I get here. I found the link. Okay. So for continuity, you need to know how to do these kinds of problems here. Okay. So you're going to be given a function. You're going to ask where, you're going to be asked where are they continuous? And again, like I said, a lot of things from Calc 1, your Calc 1 intuition will help you out a lot here. The only change here in 3D is just that the way you think about limits are going to change in 3D. reading some comments here. Oh, maximums and minimums are going to be a bigger pain in Calc 3. It's especially if you're looking for absolute maximums and minimums. Yeah, just you wait. You're gonna look back at what doing it in Calc 1 with fondness. Just the way right now you think Calc 1 limits are a joke. Yeah, you're gonna look back at finding maximums and minimums in Calc 1 as a joke as well. So yeah, don't worry. Yes, that function should be, we're going to make that function our theme, x squared y over x squared plus y squared. Yeah, it's going to be, we should get that on a t-shirt. Should like everyone in the class just wears that as a t-shirt and we'll all just be like, yeah, you should have been there. You're not going to get it. You're like, why do you have that function on your shirt? You won't get it. You have to be a part of the crew. Yeah. And then we put like that Joker meme on it at the same time. You wouldn't get it. I could totally do that. Like just put that function and then put the Joker picture below it. You wouldn't get it. you had to be in the G8 section of 212 to really understand what this function means to me. You know, it taught me shame. It taught me to pick myself up. It changed my whole outlook on life. All right. Other than that, things work out pretty straightforward. Continuous. So this is continuous if x minus y not equal to 0, i.e. x not equal to y, right? So you would say continuous on wherever the denominator is not 0. So that's still true. All x comma y. Again, you can't write it as an interval such that x is not equal to y. So that would be this one. That one's sort of obvious. Similar to this guy, that's our guy. The G8 spirit animal. All right, so notice again, similarly, can't have x squared plus y squared equals 0. This means x comma y cannot be 0 comma 0. But other than that, we'll be fine. So we can say this is continuous on the set of all x comma y such that we're not at the origin. And here's what I want to show you, because you are going to do more of this in the next class. So check this out. So when it comes to those t-shirts, we're going to have the function, we're going to have a picture, and we're going to be like, yeah, you wouldn't get it. Because now when it comes to actually looking at the picture, check this out. So here's a website, and I'll post a link. Hopefully you can see that. We can actually plot 3D. You can zoom in, you can zoom out, you can rotate, right? So this guy, you might have remembered, is our potato chip, is our Pringles potato chip. That is the hyperbolic paraboloid. Now, we can type the equation of our spirit animal to see what it would look like. X squared times y. I think you need to put the asterisk here. X squared plus y squared. I don't know, do I need parentheses here? see, x squared y, or x squared plus y squared. Maybe I was imagining a different picture. That's not the picture as I remember it. Or maybe I was thinking of another picture. X squared times y divided by x squared. Okay. Well, I guess that's it. I was looking at another crazy picture, but it turns out like you can't really see it here. I think I was looking at another one. So the origin, you can't really see it here, but the origin, maybe it was another picture. The origin actually won't work if you try to look at where 0, 0 would be. It's where all this folding is happening, right? So really there's a hole here, but this thing is not going to pick it up. But just so you can look at what some of these guys might look like, let's look at one where the limit does not exist. What was that one we did? X, maybe that was what I was imagining. X times y over x squared plus y squared. Yeah, this is the picture I remember. Now remember this guy. That was the guy where the limit didn't even exist. Right, so the one we're looking at, why the picture looks smooth is because the limit actually existed. So I think the computer plot just plots in the limit value on its own so you won't see it. So that's our spirit animal right there. That's the picture. The guy where the limit does not exist, he's a lot crazier. He's that guy. So you can look at where the origin here, it's like there's this spike. Like all sorts of craziness is happening there. Yeah. So I just thought you'll do that, like to see that. So that's the link. Let me post it in this thing. So from that, we can see what this guy looks like. This guy looks like. Boom. Okay, that's nice. Let's get through these examples and wrap it up. So we could look at a guy like this. Where is this continuous? So you realize here, if xy not equal to 0, 0, we're fine. Right? So before, we're just looking at the numerator, right? Which is up here. We just checked that. It's continuous except at the origin. So we know that if we're not at the origin, everything is fine. But now they filled in the origin. They said, okay, when x, y, 0, 0, let's fill in the point 0, much like that graph actually did, right? So it's just like in, yeah, this is continuous for all x, y, exactly. So here, to check 0, 0, we must check if the limit as x, y approaches 0, 0 of f of x, y is equal to f of 0, 0. And we saw this is 0 earlier. This is 0 derived earlier. And this is 0 by definition of the function. So this here is continuous for all of our, continuous on all of R2. You can still use the phrase continuous everywhere. That is for x, y, such that x is in R, y is in R. So whenever you have a piecewise limit, just make sure that the pieces attach nicely to each other. And we're going to stop here. So I was going to see if we could get to partial derivatives here. We won't, but I'm actually fine with that because it's a whole other topic. So for today, just focus on limits. Make sure you got those in the bag. One last example. Again, this one is a little bit more obvious. Yeah, it's a sine function. It's a continuous. Combinations of continuous functions are continuous as long as you don't introduce some arithmetic dilemma. So here, so continuous as long as y is not 0. So it's continuous everywhere except on the xz plane. So that's something that you can do. And that's that guy. Look at that graph. Look how crazy it gets when you're getting close to the origin. Right? So yeah, in the next class, you're going to be finding absolute maximums and minimums of creatures that look like this. Find the absolute max and min of this function. Right? It's coming. All right. One other thing just I want to mention before getting out of here, even though we have like 10 or so minutes left, is something in the chat here. Yeah, the hyperbolic paraboloids, those are awesome seat designs. That's what you put on saddles, but yeah, not sure I want to sit on this seat design. Anyway, do I want to post that picture? I mean, it's hard to actually pick a nice view to put on this picture. Isn't that? I want to get you guys into the habit of starting to think about what these creatures would look like. Because it's coming very soon to a theater near you. In higher dimensions, now let's talk about higher dimensions. So we really looked at limits of two variable functions. Okay. Now, again, and you'll find that the higher up you go in math, the more this is just. Am I frozen? Okay. So you'll realize that this is true. Single variable calculus, and then there's single variable calculus, which is how things worked in Calc 1 and for the first half of Calc 2. And then there's multivariable. Single variable really is its own creature. So you think about limits in a specific way. You think about function in a specific way. You think about direction in a specific way. You think about all that thing in a specific way. Once you go to 3D, then it's better to think in terms of vectors, your limits changes, how you look at the world changes. Now, once you go higher, 4D, 5D, 7D, it doesn't matter. Beyond that, things are going to work out very similar to how they did in 3D, right? So your 3D intuition will help you with 3D and anything higher, right? So how you think about limits and all that stuff, you would think about in the 3D context. So there's not only two directions, you think of in infinite directions and all that good stuff. So once you learn 3D, you will learn how to do ND. Once you learn how to deal with vectors and thinking of functions in terms of vector functions, then going to a higher dimension is just adding another component and the math stays the same. You will notice that jumping from single variable calculus to multivariable calculus, a lot of things actually changed. The way we write things down changed. Back in single variable, y equals x was a line. Now it's a plane. It's a completely different thing. The notation changes, everything changes. However, once you understand limits as I'm presenting them now, limits in higher dimensions than this, 3 variable functions, 4 variable functions, you would treat it exactly the same way computationally. And so here I just went through and I redefined stuff, the limit in terms of vector functions. So we can think of things being in Rn, n-dimensional space, where our variable is really just a coordinate of a bunch of variables, n variables. And then the a comma b becomes a1 comma blah, 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 all the way up to an, right? However, the definition is going to be thought of the same. We can still use the squeeze theorem. We can still do all that good stuff. So our intuition at the 3D level is actually going to help us out with the higher levels as well. So once you really learn things in 3D, once you cover Calc 3, you're going to be able to go and do higher things. Now you're going to have the tools to go into differential equations and partial differential equations and all these things that would live into a higher dimension, some sorts of complex analysis, dynamical systems, all that good stuff, and just higher dimensional things in general. You will have a nice foundation. So Calc 3 is really the foundation. Half of Calc 2 now as well. Is really the foundation for all your higher dimensional calculus endeavors. You kind of think of these things in two different ways, but once you learn this way, you learn all higher dimensional ways. So I just want to put a definition in here and just say, you know what, exactly what I've been saying. If you go into a higher dimension, same thing, just now think of this in terms of vectors. You have one more component to worry about, two more components to worry about. But we're going to wrap up there. Next time, which is on Friday, we are going to talk about derivatives in higher dimensions in the partial sense. We're going to talk about partial derivatives. That's the last thing we're going to talk about. And so look forward to that on Friday. And I will let you guys know what time we're meeting on Friday tomorrow. I'll give people a little bit more to. I wouldn't say Calc 3 is harder, especially with the way the syllabus is now arranged. I think you have a good foundation now to actually jump into Calc 3. So before, it could have been harder, but now I feel like Calc 2 is harder. Yeah, so because the intuition, the foundation we've just built up until this point is going to serve you well moving on into the future. So again, just to wrap up, make sure class on Friday. I'll let you guys know the time tomorrow. The final is on Thursday, May 21st at 3:30 p.m. It will be through Blackboard. We will run a sort of trial run of this on Friday as well. Last test is next Wednesday. I'll post a review for that tomorrow. That's kind of it. You can check out that link to do the graphing. These pictures, look, you can, if you're curious, look at some of these pictures that we had before. And yeah, I think we can wrap up there. Right, nothing else to talk about. So we have one more section to finish. We're going to finish that on Friday, but that ends our discussions on limits. So the things you want to know is how to show that a limit does not exist and how to show that a limit does exist. Then you should be aware that a lot of your Calc 1 methods work, and you can apply polar coordinates in creative ways here as well to kind of break things down. That being said, we're going to stop there. I've been rambling too much so far. Yeah, I really do need to take it easy tonight. Okay, so we're going to stop there. Hopefully that was fun. Okay, all right. Take care, guys. As always, I'll post the video and the notes on YouTube, and you guys will have the link. And on Friday, we'll be done with this whole thing and into review mode. That being said, I'll see you guys. Take care. Be safe. Ciao.